Hey class, me one final time, Diet Cherry Pepsi again. Same shirt. I'm filming all these on the same day before I vacate my office and go fully remote over the weekend. But I'll be posting these at different times. So this is part 4 of the Geology of Mammoth Cave review, and hopefully you all recognize the regional map that we've had in the classroom, because I know you spent hours staring at this and thinking about it and thinking about what it all means. Just to orient you, I know you can't see it too well, but I wanted to start here. All these orange squiggles are the 412 miles of Mammoth Cave. If you can make out the blue line here, that's the Green River, which of course, as we know, is the master drain. It's what controls the Mammoth Cave Formation. The green line, if you can make that out, that is the national park boundary. And then we have things like Interstate 65 coming down here, and some of these black lines are trains. The other roads, we have Cave City, where we got on and off the highway. We have Park City, where we saw the sinkhole plain, and you see all these little dots are some of those sinkholes that we saw on our geology day. And then up here you have series of ridges that have valleys in them as well. But this is the, starting right on the edge of Park City. You see the ridges that protect the cave system. So that's just to remind you. And again, what's happening is all of these sinkholes are collecting water regionally, and they're dropping the water down to the active cave level. And then there's underground rivers that pass through, pass under the sandstone ridges and come out in different places here on the Green River. This is Turnhole Springs right here. There's a spring here. This is Echo River Spring here. No, I'm sorry. This is Echo River Spring here. This is River Styx Spring. Great Onyx Spring is over here somewhere. So there's different underground rivers that collect water from the sinkholes and collect water from this area and drain them into the Green River this way. So that's the regional picture from a map view. But if I turn this around, hopefully my best whiteboard drawing ever will show you what's happening regionally in profile view. So out here, sinkhole plain. Here's Park City. That's where we went and looked at the sinkholes. So here's some sinkholes down here in the sinkhole plain. Water drains into them, gets into an underground river. And I apologize that I only had the one color of marker, or else I would have filled in different colors of different things here. But this is a really good regional picture. It's still a cartoon. I don't want to give you the feeling that when we were here at Allah's Bower, because I'm going to call that Allah's Bower, that we were right under level A. That's not true. It was in a different area, but this is a good cartoon of what's going on regionally. Cave City, in Mammoth Cave. Again, sandstone and shale caprock, then a thick, pure layer of limestone with 4 A, B, C, and D levels of cave making its way through this block of rock. And you notice I've drawn it so that it's just slightly tilting from Park City towards the Green River. Again, that's at about a 1% tilt, all the rocks in the region. As the Green River cuts down, you get the different levels of the cave. We talked about that in part 3. And one thing I want to talk about, and I meant to talk about in part 3, but I was having so much fun with that I forgot, is the sediment fills. So we talked about this on the field trip a little bit, but in addition to just the Green River cutting down, creating new cave passages as it went, you also have these things where, for some reason, the Green River water level actually goes up. In between these major cutting periods, the Green River actually goes up, and the whole region fills up with sediment. The whole thing backs up like a clogged drain, and you get sediments filling the sinkhole plain, and you get sediment filling the cave inside in the caves. And it's from that sediment, of course, that we get quartzite nodules. And this is from Utah, not from Mammoth Cave, but this is a huge quartzite nodule that appears in a different kind of rock out in Utah, but a huge quartzite nodule. But in Mammoth Cave, you find little teeny tiny quartzite nodules in the sediment fill, and that can be used to date when that quartzite nodule got buried and using radiometric dating. And so those quartzite nodules from the sediment give us the dates that I was going over in part 3. But what's really interesting here is that during the 10 million years that level B was forming, you not only have all of this cave eroded out, you have it filled with sediment once, and actually that sediment fill includes Collins Avenue. All of Collins Avenue up at the top of the cave system also gets filled with sediment at the same time. Then it empties out, and then it fills up with sediment again. And you have to understand that when I'm talking about sediment fill, it's not just filling the cave, it's filling the entire region with sediment. Again, like being a backed up drain. And so that gets filled up with sediment, and then whatever caused that environmental event to back up the drain of the Green River, it goes away, it drains out, it fills all the way up to the top of the cave system again with sediment, and then it drains out, and then finally you start getting level C and level D. And level C and level D have minor bits of sediment, but that's probably just from regular flooding at the time, not a major shift in what the Green River is doing. Whereas during the 10 million years of level B formation, you have the Green River and the entire environment of the region over those 10 million years going through some really radical changes. At one point, it's a very arid climate, and a lot of the sediments might have been windblown that filled up the sinkhole plain and filled up the cave. So it's a very interesting thing that was going on there. Again, for 10 million years, that's a long time for this to develop. So the one thing that's not on here yet, these are all the levels, but then you have the canyons that go in between the levels. So, you know, on our geology trip, Geology Day, we slipped behind Giant's Coffin, and we went through a canyon known as Dante's Gateway and got down to Black Snake Avenue on level C, and then we went through Fat Man's Misery and went from level C to level D. So all through here, as these caves drain, there's going to be canyons that cross the levels and form passageways that work down towards from one level to the other. So when we're talking about level A, B, and C, A, B, C, and D, those aren't necessarily the canyons that cut between the levels and connect the levels. It's just the main passages that we can trace at those elevations, 690, 600, 550, 500 feet elevations. And then we have these, if you remember, I mentioned the word vadose canyons that basically once the Green River drops, level B has to drain, so it forms a canyon down to the new level. Once the Ohio River comes into place and level C needs to drain into level D, you get a canyon that forms down to connect level C and level D. Again, the water trying to get to when you're above the water table, the water trying to get to the water table as quickly as possible forms those canyons. So we got this huge regional picture of Green River going up, it filling with sediment, Green River going down, it filling with sediment, it going down again, it filling with sediment again. Taze River comes in, it goes down once and for all and forms level C. And then once the Ohio River comes in, you have a final Green River drop and start forming level D. And then you have the canyons between those that drain one level down to the next level. And again, I've thrown things on here from our previous lectures. If you have a crack in the sandstone, you get a vertical shaft, and vertical shafts are also good ways to move from one level to another. And you have a vertical shaft over on this end too, where the sandstone caprock has completely broken away and you have water falling directly onto the limestone. You get calcite formations. This would be very, very similar to the frozen Niagara area. Over here on the other end of things, towards the Green River, you have a complete breakdown of the caprock. That would be very similar to Olive's Bower. This might be similar to Side Saddle Pit and Bottomless Pit. Things of that nature. So all these things we've talked about before, and then where the capstone is good and solid, you have the gypsum in both level B and level C. Typically speaking, level D is far too wet and prone to occasional flooding to have gypsum. So down here in the bottom of these level D loops, you have things like the River Styx and the Echo River, and then that's comes out on the surface, and we saw this on the field trip. It wasn't a very good view of it because the water was so high, but we saw the Echo River spring come out of the side of the wall, come out of the cave, and run across the surface into the Green River. And that kind of finishes up our regional geology picture. So again, from rain coming down into the sinkholes at Park City, to flowing through the cave and out someplace like Echo River Spring and into the Green River. That's kind of the story of the formation. But you see this big question here. Why is it the longest cave? A couple reasons for that. You have a nice, big, thick, relatively pure limestone that's easy to dissolve. You have a nice caprock of the sandstone above it. Just good, thick sandstone that forms a really great protection for the cave system for many miles. You have the rocks ever so gently dipping towards the Green River, and that makes it perfect because the water can say, hey, I'm heading towards the Green River. I don't need to rush things. I can go along this dip and take my time getting to the Green River instead of like trying to cut across the rocks. What's interesting, and it's going to be just off my diagram here, but this dip continues on the other side of the Green River, and you do have small caves on the north side of the Green River, but it's working against dip. So you might have a cave entrance, but then the water has to cut across the dip to get to the river as soon as possible. Whereas out here, it can say, oh, I'm on a nice 1% grade. I'm just going to lazy float down the river until I hit the Green River. So nice caprock, nice thick bed of pure limestone, just a perfect like 1 degree dip that the water can just hang out on and love from the sinkhole plain out to the Green River. And that's what really is responsible for creating the longest cave. You also have, about 12 million years of cave formation, which gives you 4 different levels, canyons between the levels, vertical shafts between the levels. So that provides lots of opportunity to connect passages where, level B by itself, we only saw the one passage of level B, but there's actually several level B passages across the Mammoth Cave system. And if it wasn't for the other levels and the canyons connecting them all, those other level B passages would all be separate cave systems. But because it has time to develop this complexity that connects all the cave together, then you can walk from one level B to a different level B if you try hard enough. And the same thing with the other levels too. By themselves, there are several different level C passages. If those were the only passages in the Mammoth Cave system, they would all be separate. But because of the time it takes that it has to develop, because of the solid roof over its head, you have time to create a complex and interconnected cave system that equals currently 412 miles. I wouldn't be surprised if in your lifetime we're looking at 600 miles sooner or later. So that's something to look forward to. So that's the grand regional picture of how Mammoth Cave develops and why it's the longest cave, things of that nature.